Hello, this is Mr. Waters, and this is another edition from Waters Studios, and we're going to talk to, this is a part, basically the second part of our study of integrals. And in the first part, remember that we mostly spoke about derivatives and antiderivatives. And we said that on the subject of derivatives and antiderivatives, if you started with a function, capital F of x, we called it, and you took the derivative of it using one of the various derivative formulas that we studied, you could work the problem backwards. In principle, starting with that derivative, which we called little f, you could work backwards to find the original derivative, the original capital F function. And that capital F function would represent, in relation to little f, would represent the antiderivative, right? And we even generated one kind of short formula that would help us do that for power functions, right? So, we also talked about some of the situations and some of the areas in which you would use, in which we'd be interested in integrals, very briefly. Okay, so here is another piece, the second piece to working integrals. The first piece was the idea of calculating an antiderivative, right? And the process of actually doing integrals and solving problems with integrals, generally speaking, will involve calculating an antiderivative. But what are you doing that for, and what does that get you? Well, that's what this piece is going to be about here, and it has to do with areas under curves. And in the last video we talked about, well, by areas under curves, we said that, okay, one of the major problems that calculus solves are to find areas and sums and accumulations of things, right? And I gave you some examples of that. So here's an example, a more specific example that we're going to spend a little bit of time here on. And this has to do with finding, as it says there on the sheet, calculating the total distance that a car will travel in a given time, for a given time. Well, okay, so let's say that we happen to know that this car is traveling at a speed of 50 miles per hour. Now you're thinking, well, okay, Mr. Waters, if we know the speed, it's pretty easy to calculate the distance. All we do is we just use the distance formula, right? So for instance, we've got distance equals to speed times time, right? And so, for example, the distance for 1 hour, if we travel for 1 hour, that's 50 the speed times 1 hour. That would be 50 miles total. For 2 hours, it would be 50 times 2, right? 50 miles per hour times 2 hours will give us a total of 50 miles. Or if we traveled for 3 hours, just to beat a dead horse here, that would be 150 miles, wouldn't it be? Okay, now you're saying, okay, well, that's cool, but, we sort of already knew that. We've got the distance formula, so what? Well, let's see. Well, let's make a graph of that over here. When we worked with these functions before and concepts before, we often made a graph of them. So here on the graph, at 0 time, we've gone 0 distance. This is a graph of distance versus time. 1 hour, we went 50 miles. 2 hours, we went 100 miles. 3 hours, we went 150 miles. And we could actually just sort of, draw a straight line through those dots, right? And that's a graph of the function which calculates the distance for any given time, given that the speed is 50 miles an hour. And we said, oh, yeah, that function is y is equal to 50t, right? And then we spent some time thinking about this. We said, okay, so the slope of this function here, the slope of this curve, that's the rate of change. And the speed, that's the rate of change. That's what the speed is, right? It's the rate at which the distance changes, or in this case increases, with respect to time. And it's increasing at a rate of 50 miles per hour, right? So that 50 is the rate of change, which is a speed, which, as you can see here, by no coincidence, is the slope of the curve, over 1 up 50. It's a constant speed, so the slope is always 50. And we said further, oh yeah, so that means that the derivative, the instantaneous rate of change, the speed for any given time, would be 50 miles per hour, right? Which is the derivative y equals 50 is the derivative of y equals 50t, which gives us the speed. Okay? Now, so that's starting with the distance graph and working towards speed. But remember, on the last unit, the last video, we talked about antiderivatives. We talked about, well, okay, what if we're starting with the derivative function and working backwards to get the larger function, which was the antiderivative of it? So that's what this unit is going to be about. So we're going to make a graph here. The second graph is not the distance, but a graph of the speed with respect to time. Well, the speed is always 50 miles an hour. So at time equals 0, presuming that we're starting the clock, t equals 0, at a point when the car is already going 50 miles an hour. Okay, so the speed is 50 miles an hour at 0 hours. At 1 hour, it's 50. After 2 hours, it's still going 50. After 3 hours, it's still 50. 4 hours, 5 hours, it's always going 50 miles an hour, right? Cool. Well, I'm just going to go ahead and draw a line through that, and that gives us, we called it a constant graph because it's a constant function. Oh, look, that's the graph, in fact, of y equals 50, a horizontal line, right? So, which is the derivative of the upper function, right, the distance function. Now, we see here, what's the derivative of speed? Well, that's acceleration. And you can see here that if we're just looking at the speed graph here, we see here that the slope of this is 0, right, because it's a horizontal line, which is not surprising, since if the speed is constant, the acceleration is equal to 0, right? Okay, so anyway, but we're not interested in taking the derivative. We're interested in effect working backwards. We want to know what's the total distance. We know where the distance is on this graph. Where's the distance on this graph? Well, here it is. If I start at time equal 1, that's 1 hour. And I'm going to draw a little dashed line, a boundary line, up to the top of that, right? So what we've got, as you can see, is a kind of rectangle there, right? And this rectangle has a length of 1 and a height of 50. Now, what's the area of that rectangle? Well, the area of the rectangle is 1, the width, which we're going to label mysteriously delta t, and then the height of this rectangle, the length of it, that's 50. Now, we're saying delta t because we're calling this interval here, this width delta t, because it's the change in time. It's the increase in time from starting at 0 and going up to 1. So, what's the area of a rectangle? Well, the area of a rectangle is length times width, isn't it, right? So, if I find the area, that is the amount of space in here, by multiplying length times width, I'm going to multiply 1 on the bottom, right, by 50 the height. 50 times 1, the area of that is 50. Now, what if I want the area of the rectangle from time equals 0 to time equals 2? Well, I'll put a boundary line up here. Now we're talking about a rectangle that's got a delta t. This delta t was 1. This width, the delta t, is going to be equal to 2 because, see, it's 2 hours. From 0 up to 2, it's a change of time of 2 hours. The height, though, is still 50. So now the area of this rectangle is 50 times 2, which is 100. Now I hope you can see by now that when I multiply the length, or rather the width, times the length of these rectangles to get the area, that's the same thing as multiplying the speed times the time to get the distance. So here's the big picture. Here's the thing we want to know here, is that where does distance appear on this speed and time graph? It appears as the area under the curve. That is, the area under the speed graph, which happens to be a straight line, for a given time interval, is the amount of distance that car traveled in that time. Okay? Well, what if we wanted to do it? See, this is length times width. Length times width. It's the same thing as speed times time. And either way, it gives us the distance, doesn't it? Okay? It's very important. So if I start with the speed graph here, the area under the speed graph for a given length of time, that's the total distance traveled, because it's just, we're calculating the length, and the length times the width is the same calculation as speed times time. Okay? Now, we could go out to 4 hours. Yeah? Put the boundary out to 4. Right? Delta t is now 4. So the width of the rectangle is now a total of 4, right? And that's 50 is the height. So now it's 50 times 4 is equal to 200, and that's 200 miles. So the area here, the area of that rectangle from 0 to 4 under the curve represents the total distance traveled. Okay, so we can calculate the distance, the total. We can total up the distance that the car is traveling by calculating the area under the curve. And that's one of the main problems. One of the main kinds of problems that calculus solves are calculating totals of things, totaling things up. Now, let's say I pick, I don't know, some random number x out here, or rather some random value t. And we can see that this distance from here, 0 out to t, that's just in general, whatever that elapsed time is, that's delta t. So the distance is going to be equal to 50 times whatever delta t is. More about that delta t later. But you can see that here, that delta t for us right now is that elapsed time on the bottom. Now, you're thinking, why do we talk about delta t? Why don't we just say 50? Why don't we just say 1, 2, 3, and 4? Because those are the amounts of times. Well, because we might want to know how far does the car travel, say from hour 3 to hour 5. I'm going to do this in green. Say from hour 3 up to hour 5. Right? Well, that's still a rectangle, and its width is still delta t, right? But you can see delta t is equal to 5 minus 3, which is 2. So this delta t is the idea of an elapsed time, the ending time minus the initial time. So that is going to be 5 minus 3, which is 2. So this elapsed, so that total distance traveled, we would say, is 100 miles from hour 5 until hour 3. Okay? Now, this is I guess actually part 2 of our area under a curve examples, but I'm going to cut this one off right now, and part 3 will be the much more obvious and common situations where the car is not traveling at a constant speed. How do we get the area then? All right, see you soon, or hear you soon, or something.